Hi everyone. In this video, we are going to discuss about a mechanical rotational system modeling. As we already discussed in the last lectures, what are the guidelines we have to follow while modeling mechanical rotational system. So first step, we have to assign the displacement for each node, and after that the free body diagram has to be drawn, and using a Newton's second law we have to write the force balance equation. Then you have to take the Laplace transform, rearranging that S domain terms, you will get a transfer function. Let's see an example of mechanical rotational system. So here the problem is, write the differential equations governing the mechanical system shown in figure and determine the transfer function. This is the mechanical rotational system for which we have to compute the transfer function, means that output to the input. Output is basically an angular displacement and the input is basically, it is a torque. So we have to find the theta of S divided by T of S. So for this system, we have two nodes, one at J1, another one at J2. So we have to draw the free body diagram at J1 and J2. And for the mechanical rotational system, we are applying torque as an input. So this is the free body diagram at J1. Here the applied torque and the angular displacements associated with J1 is represented by means of an down arrow. Whatever the opposing torques introduced is represented by the up arrow. So for this J1 we have an applied torque, so it is T. Due to that there is an angular displacement, that is theta 1. We know that this mass, that is a moment of inertia, will produce some opposing torque, that is Tj1, and we have a spring that will introduce an opposing force, and B12 that will also introducing an opposing torque. So we will see what are the opposing torque equations. So Tj1, it is governed by J1 d square theta 1 by dt square. Tb12, it is b12 into d by dt. Why theta 1 minus theta? Because this dash part is available between two nodes, so there will be a displacement at both the ends. Then we have a Tk, which is equal to k into theta 1 minus theta, because we are considering J1, so it is theta 1 minus theta. Using Newton's second law, we can write sum of applied torque is equal to sum of opposing torques. We have three opposing torques and applied torque is T. So we are substituting all the values here. So your equation becomes J1 d square theta 1 by dt square, and B12 is Tb12 is B12 d by dt theta 1 minus theta plus k into theta 1 minus theta, which is equal to torque. Now this is the equation, and we are taking the Laplace transform for this equation. Wherever you find d square, we have to represent s square, and wherever we find d by dt, so if you take a Laplace transform, it is s. So it is J1 s square theta 1 s, B12 s into theta 1 of s, B12 s into theta of s, k into theta 1 of s minus k into theta of s. When we take a Laplace transform of t, it is t by s. In this terms, the theta 1 is available. So we are taking commonly theta 1 outside. So we are taking theta 1 outside and we are taking theta of s outside. So this is your equation number 1. Next, we have to draw the free body diagram at J2. For this moment of inertia, there is no applied torque, so we don't have a T term. However, because of this torque, this will rotate, so whose angular displacement is theta, and we have 3 elements connected together, and J2 itself will introduce an opposing torque, so it is not Tj1, it is Tj2 and Tb, Tb12 and Tk. Opposing torques are Tj2 is equal to J2 d square theta by dt square, Tb12 equal to B12 into theta minus theta 1, Tb equal to B into d theta by dt, Tk is nothing but k into theta minus theta naught. So using Newton's second law, so we are adding opposing torques and the applied torque is equal to 0. So we are substituting, we will get this equation. Now this is the expression we know. We are going to take the Laplace transform for this equation. We will be getting a Laplace transform, and here we are taking theta of s outside from these terms. We will get s square J2 B12s, and here it is BSO, B12 plus B into S plus K, and similarly theta 1s we are taking outside from these two things, so it is B12 S plus K into theta 1 of S is equal to 0. So from this we are computing what is theta 1 of S. So this is equation number 2. Now we know that equation number 2 and 1. So we are going to substitute this theta 1 of S in this particular equation. So we get theta of S into this term. Additionally, this J1 S square term will also come, minus theta of S B12s plus K equal to T of S. Here what we are doing is we are taking theta of S outside, and also we are doing a cross multiplication. We will get this term, and from this we are computing the theta of S, that is output displacement divided by the applied torque. This is the transfer function of the given mechanical rotational system. So these are the references. Thank you.